Good morning, dear students. Welcome back. I am your physics professor, Dr. Nagraj. So I am continuing with module 3, model question paper number 1. Module 3 is about quantum computation. Here also you will have two full questions, out of which you have to answer any one full question. Question number 5 and 6. 5 and 6, out of which you have to answer either 5 or number 6. Okay, and as usual, this is a question paper pattern. I am going to discuss about these questions. That is module 3, quantum computation. So 5, 6, next will be 7, 8, and the last will be 9 and 10. Well, the pattern as usual, 3 ABC or 4 ABC, C, and this in this particular module I cannot say C is numerical problem, B is descriptive, A is descriptive. It can be anywhere, because as you all know, this module consists of numericals as well as derivations and explanations, as well as matrix multiplication, matrix addition, something like that. So therefore here C need not be a numerical section. Look at these marks allotted. Here 8 marks allotted for C in this particular question, 6 marks allotted in 4C. Okay, first question. Discuss the working of phase gate, mentioning its matrix representation and truth table. So whenever you are asked to answer gates, you write 1 or 2 lines about the gate and then its matrix form and then truth table, if possible circuit symbol, and then 1 or 2 operations like operating on ket 0, ket 1 or ket psi, like that. So this one, phase gate, is also known as S gate. It transfers 0 to 0 only. Ket 0 there will be no change, but 1 changes into I ket 1. So ket 1 changes to I ket 1, and it is represented as this is a matrix form. Phase gate is represented by S is equal to 1 0 0 I. So you have to remember matrix form of each and every gate. Okay, now let us operate it on ket 0. S is operated on 0. So S is 1 0 0 I. 0, ket 0 is 1 0. It is a column vector. Now you do the matrix multiplication. 1 into 1 1 plus 0 into 0 0. So first row is generated. Second row, 0 into 1 0. I into 0, I into 0 here. So 1 plus 0 1. 0 plus 0 0. So I finally end up with 1 0. That means when S operates on 0, it remains undisturbed. So I have 0 only. Now let us go to S operating on 1. When S operates on 1, write S matrix and ket 1 matrix, that is column matrix 0 1. And keep on simplifying. This is self-explanatory. Okay, so multiply first row, first column, second row, first column, you generate this particular part. So I end up with 0 and I. Now you take I outside, then it becomes 0 and 1. So I into 0 1. 0 1 is nothing but ket 1. That means when S operates on ket 1, I end up with I ket 1. So this is what in the definition I mentioned. So phase gate is a gate which transfers 0 to 0 and 1 to I 1. Right. So with this I now go to the operation on the superposed state, alpha beta. When I have alpha beta, alpha remains as it is. That means 0 remains as it is. Beta becomes I beta. So beta is I beta. This is the output. Okay, now comes the truth table. Truth table, input 0, output is also 0. Input 1, output is I ket 1. Input is alpha plus beta, output is alpha ket 0 plus I beta ket 1. So that's all about phase gate. Like this there are many other gates. Please practice other gates also. Don't think that only phase gate is going to come. This is, after all, it is a model paper. Okay, so questions will be like this. Please try on Hadamard gate also. There are multi-qubit gates also, not only single qubit. This is actually single qubit gate. You have even multi-qubit gates also, like C0 gate, C0 Z gate, swap gate, Toffoli gate. All those things you practice. Okay, well, next comes explain orthogonality and orthonormality with an example. Orthogonal means two vectors perpendicular to each other. Orthonormal means not only perpendicular, when the inner product is taken on the same vector, answer must be 1, normalization. So perpendicular means orthogonal, normality means product is 1. If both are combined together, it should be orthonormality. For that I give examples. First, what is orthogonality? Orthogonality andre ಏನು? If inner product, dear students, inner product is almost similar to dot product. You please watch my quantum computation videos on inner product and normalization, orthogonality, all these concepts. If the inner product of two vectors is equal to 0, then they are said to be orthogonal or perpendicular to each other. Now let us take two vectors, ket 0 and ket 1. Ket 0 is 1 0, ket 1 is 0 1. Now I take the inner product. Inner product is brach multiplied with ket. So ket 0 convert into brach. How to convert ket to brach? I already explained. I hope you know this. Anyway, I will explain it once again. See, this is brach. Okay, so it will be having 1 0. If I want to write the ket of this, what to do? I change row column to row. At the same time, I have to take the complex conjugate. Of course, there is no complex number here. Therefore, there is no question of taking complex conjugate. Similarly, ket 1, I want to write in the brach form. Ket 1 is 0 1. In the brach form, I want to write. Then it will be 0 and 1. So like this. So brach to ket, ket to brach. Ket to brach, what to do? Convert rows to column to row with complex conjugate. Well, now coming back to this particular question, see this. I have 0, okay, 0 1 0 1 0 1. Now I take the brach of 0. Brach of 0 means 1 0 row, column becomes row, 1 0 0 1, multiply 1 into 0, 0 into 1, finally it comes out to be 0. That means inner product of 0 and 1 is 0. Therefore, 0 and 1 are perpendicular to each other. That means ket 0 is perpendicular to ket 1. Therefore, 0 and 1 are orthogonal. This is one thing. So, if each, next orthonormality. Now coming to orthonormality, orthogonal aito. If each element of a set vector is normalized. Normalized andre eno, when you take inner product of the same vector, answer must be 1. Like, I show you, like if I take inner product of 0 on 0, if it is equal to 1, then I can say ket 0 is normalized. Okay, similarly, if I take inner product of 1 on 1, if I get answer as 1, then ket 1 is also normalized anta artha. Okay, so this is normalization. Normalization means on the same vector we have to take. Okay, now I just remove this part. Right, that's what I have mentioned here. If each element of a set of vectors is normalized and the elements are orthogonal with respect to each other, then we say the set is orthonormal. Now consider the example, 0 and 1 as usual. Now I take 0 on 0, 0 on 0. When I take, see, 1 0 1 0, okay, brach 0 is row 1 0, ket 0 is column 1 0, multiply 1 into 1 1, 0 into 0 0, so 1 plus 0 is 1, so that is normalized. This is what I told you. So inner product of the same vector is normalized. 1 andre it is normalized. Now 0 is normalized. If you want, you can try for 1 also. Ket 1 brach 1 tagondu try madi, but not necessary. Now I take 0 and 1 together, which I already did here. 0 and 1 together. When I take 0 and 1 together, 1 into 0 0, 0 into 1 0, 0 plus 0 is 0, so orthogonal. That means 0 on 0 is normalized, 0 on 1 is orthogonal. Therefore, 0 and 1 together, I can call it as orthonormal. I hope it is very simple and you got it. Okay, now coming to the next question. Well, I will do it here. Given psi is equal to alpha 1 alpha 2 and phi is equal to beta 1 beta 2, prove that brach inner product of these two is equal to complex conjugate of inner product of these two, and this we have to prove. Okay, I will do it here. Just wait. First I take psi and then psi. So I take psi multiplied on phi. Psi means alpha 1 alpha 2, so this is the brach, and then phi means beta 1 beta 2, Okay, so that is equal to alpha 1. Yes, I have to take the complex conjugate, you know. So put alpha 1 star, alpha. I don't know whether alpha 1 is complex or real, so I have to put star. Therefore, alpha 1 star beta 1 plus alpha 2 star beta 2. I call this as equation 1. Next, I go for phi psi, that is beta 1 star beta 2 star, that means ket to brag. Ket to brag, what to do? Convert column into row and then take the complex conjugate. That's what I have done here. And then phi remains as it is, alpha 1 alpha 2. So simplify, beta 1 star alpha 1 plus beta 2 star alpha 2. Now I take the complex conjugate of the whole product. That means beta 1 star complex conjugate beta 1 alpha 1 star plus beta 2 star star beta 2 alpha 2 star. So that means for this entire thing I take the complex conjugate. So this is my next one. This is equation number 2. Now equate from equation 1 and 2. Look at equation 1 and 2 carefully. Beta 1 alpha 1 star, beta 1 alpha 1 star, beta 2 alpha 2 star, beta 2 alpha 2 star. Okay, beta 2 alpha 2 star. That means ket phi psi star is equal to phi phi. Okay, this is what we actually expected and ends the proof. This is very good question. Please practice this once or twice. So that is all about this particular question. Well, now move on to the next one. Explain the representation of qubit using Bloch sphere. Bloch sphere is an imaginary sphere used to represent single qubit states as a point on its surface. It has unit radius. North pole takes 0 level, south pole takes 1 level. Means north and south pole are used to represent ket 0 and ket 1. It looks like this. See, it looks like this. This is an imaginary sphere. In this imaginary sphere, north pole is represented by ket 0, south pole is represented by ket 1, and we have 3 dimension, x axis, y axis and z axis, and any point on the sphere represent the superposition of 0 and 1. And in a spherical system we have 3 coordinates, namely r, theta and phi. So spherical coordinates are represented by r, that is radius vector, theta and then phi. Theta corresponds to angle with zenith or z axis. Phi corresponds to angle with x axis. This is nothing but projection of the vector. So projection means it's a shadow. Its shadow falls on. Please watch my Bloch sphere video for more details. Okay. So any point, whatever I just explained is in wordings. Any point on the sphere represents superposed states. Bloch sphere allows the state of qubit to be represented in spherical coordinates r, theta and phi. It is as follows. Okay. See, theta value lies between 0 and pi. Phi value lies between 0 and 2 pi. Theta can take only from here to here. So here to here means 180 degree. Phi can take full one circle. One circle means 2 pi. That is why the limitations are 0 to pi theta value, 0 to 2 pi phi value. Now the superposed state is represented by alpha ket 0 plus beta ket 1. We can show that psi is equal to cos theta by 2 into ket 0 into plus e to the power of I phi sin theta by 2 ket 1. Dear students, please remember this equation. ಇದನ್ನು ನಾವು derive ಮಾಡಕ್ಕೆ ಹೋಗೋದಿಲ್ಲ, but we can prove, but not necessary. Please try to remember this equation. Now let us take any 2 cases, because marks allotted only 6. 8 marks allot ಮಾಡಿದ್ರೆ I could have taken 4 different cases. Okay, let us take one case. In the first case, I take theta 0. Theta 0 means, look at the diagram. So this is z axis, this is my psi. So psi is here. So theta is 0. Okay. So my project, vector representing the superposed state is orienting along z axis, means theta is 0. Theta 0, phi is also 0, because its shadow is not making any angle. So if I put theta 0, phi 0 in the above equation, this becomes cos 0 ket 0 plus e to the power of I 0 sin 0 ket 1. ಈ ಜಾಗದಲ್ಲಿ 0 ಹಾಕ್ತೀನಿ. theta by 2, theta 0 ಆಗಿರೋದ್ರಿಂದ 0 by 2 is 0. Next, cos 0 means 1, so it is 1 into ket 0, plus the next one is sin 0 is 0, so second term becomes 0. Therefore, psi equal to 0. That means when the vector is orienting along z-axis, it obviously represent ket 0 state, that is north direction, north pole. Now you take the second case where theta is now 180 degrees, so this way, so it must be ket 1. Prove that psi is equal to ket 1. So this was earlier along z-axis, now it is along minus z-axis. That is why I have taken theta as pi. Substitute for pi, pi by 2 ಆಗುತ್ತೆ, ಇಲ್ಲಿ pi by 2 ಆಗುತ್ತೆ. Anyway, cos pi by 2 is 0, sin pi by 2 is 1. So finally I have psi is equal to ket 1. So when the vector is along the negative z-axis, it is south pole representing ket 1. Like that we can take any value for theta, any value for phi, and we can represent the different states of the qubit. So this is about the Bloch sphere. Well, coming to the next question, explain single qubit gate and multi-qubit gates with an example for each. Single qubit ge ಒಂದು, multi qubit ge ಒಂದು. Single qubit there are many, Pauli's X gate, Y gate, Z gate, Hadamard gate, phase gate, like that. For multi-qubit also there are many. We have C0 gate, C0 Z gate, Toffoli gate, swap gate, etc. So I take one single qubit gate, one multi-qubit gate. For single qubit gate, I have taken Pauli's X gate, that is 0110. It is also called as bit flip gate because it will take ket 0 to 1, 1 to 0. I show you how. This is very simple. By now you are already familiar with this. X ket 0, X is matrix 0110 and ket 0 is 10. Multiply, finally you end up with 1. Andre when X operates on 0, you get 1. Similarly, when X operates on 1, you get 0. Got it? So like that, X is going to take, X will take 0 to 1, 1 to 0. So it is X form. Okay, so it is a flipping. It is flipping bit from 0 to 1, 1 to 0. Suppose if it operates on alpha beta, alpha becomes beta, beta becomes alpha, ಅಥವಾ 0 becomes 1, 1 becomes 0. ನೋಡಿ alpha 0 ಇರೋದು alpha 1 ಆಗಿದೆ, beta 1 ಇದ್ದಿದ್ದು beta 0 ಆಗಿದೆ. So the truth table is here. 0 becomes 1, 1 becomes 0, and alpha 0 becomes alpha 1, beta 1 becomes beta 0. This is about X gate. Now coming to multi-qubit gate. I have selected C0 Z gate. C0 Z gate is a multi-qubit gate. There is one control qubit. See, in C0 gate always there is one control and one target. Control is in the upper level, means second line. Target is in the lower level, first line. Control is active only if it is in the one forum and it will operate on the target. So it will change the target position. There is one control qubit and Z unitary matrix as the target qubit. If the control qubit is one state, then it acts on the target Z, and Z it will flip the state from one level to another level, that is through 180 degree. Z ಅಲ್ಲಿ 1 ಇದ್ರೆ -1 ಆಗುತ್ತೆ, okay, 0 ಇದ್ರೆ ಏನು ಚೇಂಜ್ ಆಗೋದಿಲ್ಲ. Z is a Z property. Well, the matrix form, circuit symbol, everything shown here. So this is control, this is a target. Matrix form of Z, first 0 0 0. See, it is a multi-qubit system. In multi-qubit system we have 4 elements in the line. See, multi-qubits, just I write one here. Ket 0 0, what to write? It is not just 1 0, you have to write 3 zeros. Similarly, ket 0 1 is not just 0 1, you have to write 2 more zeros. So totally there will be 4 elements. Like that, this corresponds to 0 0, this corresponds to 0 1, this corresponds to 1 0, this corresponds to 1 1. See, 1 1 actually it should be 1. Actually it should be 1. But in Z gate, that 1 changes to -1. That is what the definition of Z is. So in Z gate, one state 0 1 1 state flips to -1 1 state. Okay. Well, so 1 1, this is plus 1 becomes -1. Now this is the matrix form. Now let us operate it on any one. Well, I will operate it on 1 1 only. Well, uz is equal to 1 1. Uz into 1 1. Uz is here, 1 1 is here. Okay, when I do the operation, right? You just keep on multiplying, you end up with this answer. First column 0, first row 0, second row 0, third row 0, fourth row will be minus 1. So 1 1 becomes minus 1 1. So in C naught Z gate, 1 1 ket 1 1 flips to minus 1 1, that is called 180-degree phase. And the truth table, 0 0 remains as it is, 0 1 remains as it is, 1 0 remains as it is, 1 1 changes to minus 1 1. So dear students, gates are very important. Definitely there will be at least 2 gates, either multi-qubit gate or single qubit gate or combination of both. Please practice all the gates, and they are very simple, and I feel they are more very simple. Well, explain the matrix representation of 0 and 1 states and apply the identity operator I to 0 and 1. Identity operator is nothing but 1 0 0 1. Okay. Well, first of all, qubit definition. Let us give a brief explanation of qubit. Qubit is a quantum version of bit and labeled as ket 0 and ket 1. They are represented by two-dimensional column matrix as 1 0 and 0 1. Even ಸಾಕಷ್ಟು ಡಿಸ್ಕಸ್ ಮಾಡಿ ಆಯಿತು ಆಗಲೇನೆ. Now let us have an identity matrix. Identity matrix is 1 0 0 1. Now you operate I on 0, show that it remains as it is. See, when I operate I on 0, I end up with 0 only, 0 ket only. Similarly, when I operates on 1, so I end up with ket 1 only. That means identity operator is something like number 1. 1 into anything is that anything. Any number is the final product. 1 into any number is that number only. So this is identity matrix importance. And here I have I operating on 0, ket 0. I operating on ket 1 only. So like this you can expect questions from quantum computation. Well, I stop this video here. I will come back to you on module 4 and module 5 in next videos. Please keep watching my videos and support me. Thank you very much.